Okay, two topics today. Topic 1, bisection method, and the second topic from section 3.2, the Newton's method. Let me explain this time. Bisection method by a graph, by a diagram. The assumption about bisection method is function f is continuous on the closed interval AB. But this condition, in practice, very difficult to verify this condition. Usually, we don't know, given a function, we usually don't know the function is continuous. But here, we just assume function f continuous. And also, this function has different sides at the two endpoints. In this diagram, the function at the point A, left endpoint, the side is function value is positive. And at point B, the side of the function value is negative. So then by intermediate value theorem, it is guaranteed on this interval AB, there must be at least one root or one zero. Okay, now bisection method. First step, take the midpoint of the interval AB. Say midpoint is about here. Midpoint, C, the midpoint. Then compute function value at the midpoint and compare the side of the function value at the midpoint with the two endpoints. Say compare with the side of the function value at the point A. Clearly, in this diagram, the sides are different, right? Function value at C is negative. Function value at A is positive. Therefore, there must be one root in this left half subinterval. After we know there must be a root in the interval AC, then we rename the point C as B. Then we have a new interval AB. This new interval is half the length of the original interval AB. Okay. And now continue to cut interval in half. Now cut AB, this new interval, then midpoint about here. C. Then compute function value as C and compare the side of the function value as C and the side of function value at A. In this diagram, we still have opposite sides, positive, negative. So the root is in this new interval AC. Now I rename C as B. I have a new interval AB. In this new interval AB, I pick midpoint. Yeah, midpoint C here, C here. Now compute function value as C. Then compare the function value, the side of the function value with the side of the function value at A. Now this time they have the same sign, both are positive. Therefore, the root must be in this interval C, B, CB. Now this time I rename this midpoint as a new A, Now I have a new interval AB, new interval. Now cut the new interval in half. Pick midpoint C, Then compute function value at this point C. Then we will see function value at A and function value at C, both positive. Therefore, the root must be in the interval CB. Now we name this C as A. Then we have a new AB. Now pick midpoint C. Then from this diagram, we can see that CB, this subinterval, still contains arrow. Then this C is a new A. This is the idea of bisection method. Cut interval in half, and then produce new interval AB. This new interval AB always contains a root of this equation. We are solving this equation. Okay. This is the idea of bisection method. Now, a electron question. Question is, okay, we use the midpoint as an estimate of the root arrow. We use the midpoint C as an estimate of the root arrow. Now the question is how to know C is close enough to arrow. How to know? If C is close to the root arrow enough, then we stop and consider C as the solution. There are two criterions, okay? Criterions that we can use. The first one is test whether the function value at the point C in absolute value is small enough, say less than epsilon, some number, epsilon, right? Yeah, less than epsilon. Epsilon is provided by the user of bisection method. Okay. If the user wants epsilon small, say 10 to -7, then epsilon is -7. Epsilon is a small, very small number. Small number. And of course, positive. One criterion is if the function value at C in absolute value is less than some small number, then we stop and consider C as the solution. The second criterion is if the interval AB, the length, absolute value, right? A minus B, absolute value, less than some number, delta. Delta also provided by the user of bisection method. And it is, again, a small number. This is a small number, If the length of the interval AB is small enough, then we stop and consider the midpoint of the interval AB as the root. Please note that midpoint of the interval AB is inside the interval, right? Inside the interval. And also the root inside the interval AB. If you draw a number 9, AB here, midpoint here, root is here, then we can see that C minus arrow absolute value, this is the distance of C from the root arrow, not greater than 1/2 of the length of the interval AB from this diagram, right? B minus A, right? Okay. So when B minus A is small enough, less than delta, then it is guaranteed the midpoint is also very close to the root R, less than 1/2 delta. So usually we adopt these two criterions to stop running bisection method. However, these two criterion, they are not perfect. In some extreme case, when function value at C is very small, the midpoint C can be very far from the root. Say, for example, take a look at the following diagram. Okay. Here, the argument is function value at C less than epsilon. Okay, doesn't imply C is close to R in some extreme case. Say, for example, take a look. Okay. Here. R is here. Now the function is flat, very flat, near the root R. Very flat. Very flat. This is an extreme case. The midpoint, say midpoint is here, C. In this case, function value at C is small, but C is still far from the root R. So this criteria not perfect, cannot handle all the situations. Okay. Now the second case. Okay. B minus A. The length of the interval is small. Also doesn't imply that the midpoint is close to the root. Let me show you one diagram. Say this diagram here. This diagram. Okay. The function has this vertical line as a vertical asymptote. The graph of the function up to infinity, then down to negative infinity. Yeah. Of course, this function is not continuous, but we just assume the function continuous. But in practice, usually we don't know. In some cases, we don't know whether the function is continuous. Okay. The interval is small. Say, let me pick a small interval. Say, interval here, A, B. This interval very small. Function value at A positive. Function value at B negative. A midpoint about here. Midpoint C. Yeah. The interval is very small, but the midpoint is close to no root. In fact, this function has no root. So this criterion also doesn't guarantee. Doesn't guarantee that the midpoint is close to R. But in computation, okay, I can say that low method is perfect. Low method is perfect. Okay, now next, let me present the algorithm of the bisection method. Okay. Algorithm. Okay. Yeah. How to write an algorithm about this method? Algorithm. This is a practical algorithm. First, you need to input some data to the algorithm. First, the interval AB, you need to give the algorithm the interval AB. And then M is an integer, positive integer, a positive integer. A positive integer. This integer, we, of course, from the user of bisection method, the user just want to run bisection method a maximum m steps. Okay, the user doesn't want to run the bisection method forever. Beyond the number of steps beyond m, stop the algorithm. Stop the algorithm. Okay. This is the a positive integer. It is the maximum a number of steps that the user permit. Okay. Yeah, the user just want to run bisection method a maximum of m steps. He doesn't want to run the algorithm forever. Okay. Then you need to input delta, a small number, and epsilon, a small positive number, both positive. Okay. Okay. Now, this is step 1. Step 2. Evaluate function value and point A. Yeah. This is x-axis interval AB here. Evaluate function value at A, then store the result in the variable U, and then evaluate function value at B, then store the result in V, and also evaluate the length of the interval B minus A, and then store the result in E. E means error. Okay. Okay. All right. Now, step 3. Compare the size of the function values at the 2 endpoints AB. Okay. Now, if psi, if psi if you write this algorithm in MATLAB, then this MATLAB function output the sign of a number, say sign of 100, then it should be 1. Sign of 0, it is 0. Sign of negative 8.7, it is negative 1. If psi of U is equal to psi of V, then stop the algorithm. Okay. We don't know in this case because the function value at A has, say, positive sign, at B has positive sign. No guarantee the function has a root in AB, so we don't know. Okay, so we stop. We don't run bisection method. Otherwise, okay. Otherwise, continue. Okay, run bisection method. A maximum of m steps. Okay, k from Step 1, step 2, maximum M. Okay. Let me erase here. Okay, now for K going from 1 to M, now E now is the length of the interval AB. Now E divided by 2, midpoint here. E divided by 2 is the length of 1/2 one subinterval, and store this new value to E. Now this new E is the length of either left subinterval or right subinterval here. Right. Now compute the midpoint. The midpoint is A plus this new E, right? This new E. The new E is the length of the interval AC, this new E. Now A plus E, then the midpoint. After we have the midpoint, then evaluate the function value at midpoint, and then store the value in W. Right. Now, have a check whether or not the above two criterions are met. Okay. If now check the criteria. If E, this E, okay, E is A to C, the length, less than delta, then we consider the midpoint is close to the root enough. Or W now is the function value at the midpoint, absolute value of W less than epsilon. If either these two conditions is met, then we stop running the algorithm and output the midpoint C as the root. Okay. Otherwise, okay, have a check with the sign of W. Now, W is function value at C. Compare the sign of W with the sign of function value at point A. Function value at point A now is U. Sign of U. Compare. If the signs are different, then function value at A, function value at B, at C, they have different signs. Now we name C as a new B. C as a new B. And then function value at C. Now C is B. So function value at C is function value at the new B. Then store function value at B in U and in V, right? So we store it in V. Okay. Let me continue on a new page. If otherwise, if the sign at the midpoint and the sign at the left point are equal, then the root should be in the subinterval C to B. Okay. Otherwise, else, the root now is in the interval C to B. Now I rename C as a new A. C in A. And then now C is A. Then function value at C is function value at the new A. Function value at A is stored in the variable U. So let me store this W in U. W in U. Then and the if statement is if statement. Yeah, this if statement. Okay. Right. Yeah. Then repeat the same process. How many times? Maximum M times. Okay. Now, finally, add an N. This N ends this follow. Yeah. Let me write down again. Yeah. This N ends the follow. And this N ends this if statement. If this statement. Okay. Now let me show you one example about this algorithm. About this algorithm. Okay, take a look. Okay. Example 1. Use the bisection algorithm or method to find the root of this equation. Ex is equal to sine of x. This equation may have, I don't know, may have many roots. Bisection method finds only one root, cannot find all the roots. Use bisection method to find the root that is closest to 0 to get some idea about where the root that is closest to 0 by plot the graph of the two functions. Sine, the graph is a wave. A wave. Sine. This is sine. Sine. Okay. The graph of e to x look like this. And then up to infinity. This point is 1. So from this diagram, we can see that the root that is closest to 0 is this root. On positive x-axis, low root. And from this diagram, we can see that solution. The root, let me denote the root by arrow. Closest to 0 is on the left of the origin and is contained in this interval. Which interval? -4, -3. Now I apply bisection method to this interval. Okay, the initial AB is this interval. Now, write an algorithm. Say in MATLAB, we can make the following table. Okay. K is the step number. The initial interval is -4, -3. Yeah. Okay, now C, midpoint. And function value at the midpoint. If the function value is small enough, then we stop and use C as the root. Okay. Step 1, cut the interval in half. The midpoint is -3.5. Function value 0.32, 1. Step 2, the midpoint is this. Function value is 0.694 times 10 to -1. Step 3, the midpoint is 125. Function value is some function values are negative, some are positive. The criterion take absolute value. Okay. Step 4, -3.187, 5. 0.625 times 10 to -1. Actually, bisection method is a convergence speed is quite low, okay? Quite slow, the convergence. Run. Let me skip steps. Then 13th step, the midpoint is this, and function value -3, 10 to -3. And step 14, (10 to -4), and 15, function value -0.124, 10 to -4. Very, very slow. 16, 5 times 10 to -5. If the user is happy about the function value of order 10 to -5, then stop here and use this number as the root of the solution of this equation. Bisection method actually is not fast. We can prove bisection method the convergence rate is linear. Recall that the definition about linear convergence. We have a sequence. Okay, converge to some number. We say that the convergence rate of this sequence is linear if, you remember that, xm + 1 minus absolute value, then over xn minus, compare the current distance to the distance in the previous step. Then the limit, take limit. If this is some number C, where C greater than 0 and less than 1, then we say that the convergence speed is linear. Now, bisection method, okay. Bisection method here. Usually, the midpoint, CK is the midpoint of, okay, the midpoint of AK, BK. Let me use AK, BK to denote the interval AB in step K. In step K. Okay. Usually, CK minus the root that we want to find in absolute value roughly is 1/2 of the length of this interval, BK minus AK, but not exactly, maybe multiplied by some number, say alpha. Okay, then when I put alpha, then alpha, where alpha, of course, greater than 0 and less than, okay. This is in general case, not in special case, not in extreme case. Say, in some extreme case, it happens that the midpoint coincide with the root. Then in the case, just one step, then you can get the root, not the extreme case. General, the distance between CK and R roughly is this number. Now, let me come. Now let me find the ratio. Okay. All right. Now, CK minus R. CK plus 1. CK, the midpoint is converged to the root, and then compare. Then this is a 1. This is a 1/2 alpha BK plus 1 minus AK plus 1, and then over roughly, okay, not exactly, okay, roughly, then CK minus R, alpha BK minus AK. But BK minus AK is the length of the interval AB at step K. Now, the next step, the length of the interval should be half of the length of the interval in previous step. So this is a 1/2 times alpha times 1/2 BK minus AK. Okay, now I cancel. So this is a also cancel alpha. So we get 1/2. Therefore, the convergence is linear. Bisection method, convergence rate is linear, not fast. Newton's method, in section, this is section 3.1. In section 3.2, Newton's method, the convergence rate is order 2, much faster than bisection method. But anyway, that is the story of next section. Now, let me present some basic properties about bisection method. Right? Freedom. You can find this freedom in the book. Freedom. Let A0, B0, the initial interval. A1, B1, the interval after the first step. A2, B2, the interval after the first two steps, and so on. In general, AK, BK. Below the intervals in the bisection method. Okay, and let R be the zero or the root of this equation. We are solving this equation, okay? Let R be the zero of the function f contained by these intervals. Now, conclusions, okay? Then bisection method has the following properties. Number one, AK, the left hand point of the interval, approach the root R, okay, limit K approaches infinity, okay, is equal to R. Right hand point also approaches R. A midpoint CK approaches R. All approaches R, okay. Where CK is the midpoint, CK, okay, where CK is BK plus AK, then divided by 2, midpoint. B, the root and the midpoint, the distance log greater than this number, log greater than actually half of the length of the interval AK to BK. The half is this, K plus 1 times the length of the original interval A0, B0. B0 minus A0. Very fundamental, okay, and also very easy to see these two properties. Now, let me show you one example about how to use this inequality. Example 1, example 2. Suppose that the bisection method is started with the interval 50 to 63. The initial interval is this interval. Now the question is, how many steps should be taken to compute a root. Say, let me name that root by arrow with relative accuracy of 10 to negative 12. Okay, yeah. And this question actually is asking that CK bisection method use the midpoint as the estimate of the root arrow. Okay, relative error. CK minus the true root absolute value, then over the true root. We want the relative error less than 10 to negative 12. Now, what is K can make this inequality true? Okay. First, because we don't know the root arrow, but we know that the root, this is a 50, this is a 36. We don't know arrow, but we know arrow is inside this interval. So therefore, CK minus arrow over arrow less than or equal to arrow is greater than 50. So we have this inequality 50. Right? You agree? Okay. All right. Now, for K, for this inequality true, I just need to make sure this inequality is true. Okay. Yeah. Okay. On the other hand, by property, this property, okay, by this property, okay, on the other hand, a CK minus R less than or equal to 2 negative K plus 1, and then B0 minus A0. B0, A0 is this interval, initial interval. So this is a K plus 1. B0 minus A0 is 13 times 13. So in order for this inequality to be true, we just need to make sure times 13 over 50 less than this number. Less than this number. 10 to, yeah. Okay, now solve this inequality. Then we get K is greater than or equal to 37. So when you run bisection method, at least 37 steps, guarantee CK has relative error to the true root less than this number. Guarantee. Done.